Hi all, welcome to the first video of Econometrics Never Stop Learning. And then in this case, I would like to talk about OLS regarding its concept and intercept estimation proving. Let's assume that we are working with two variables and then we are working with our samples. In this case, OLS is just the abbreviations of ordinary least squared, and then the concept of OLS is just fitting the best fitted line to represent a linear relationship between two variables. Let's draw a scatter plot to illustrate this notion. Right, I have a variable x and I have another variable y in this case. So if you notice that I have the dots, the white dots here, the circle. All right, in this case, it's just the intersections between my, let's say this is my x1 and y1 in the sample. And then this one is the intersections between my x2 and y2, and so on and so forth. And then in this case, so I have my x1, I have my y1. If you notice that the line, you can actually make another intersection here on the line. So this is what we call as the predicted y1. So there is a difference between the predicted y1 and the y1 here. That's what we call as estimation error. And then OLS is just looking for this line, the blue line, that actually can minimize the estimation error. All right, so the line could have been here, the line could have been like this, the line could have been like that, but it did not turn like that, because the blue line here is just the best fitted line that you can actually find to minimize those estimations errors. That's just the simple concept of the fitted line. All right, let me erase all of this first so that it's becoming more clear. So in this case, you have noticed that in terms of this scatter plot and then the best fitted line, there are two usage here. First, they can actually help you to quantify the relationship between x and y. Second, they can actually help you to predict the value of y given the value of x, right? And then all of these are usually represented in the form of equations of this one, right? You have yi, you have xi, you have epsilon I, right? All of these three are what we call as random variables, right? And then this one is your intercept, this one is your beta one, and then both of them are constant. All right, so that's all about it for these particular slides. Let's go to another slide. I wrote it down here again. So in this case, we are asking what is intercept and then what is beta. Let's draw again the scatter plot. Intercept is just this part, these intersections between your fitted line and then in this case with your y-axis. This is what we call as intercept. All right, so you notice that we have these white dots again, similar with the previous one, right? So in this case, I want to explain more about what is beta. Let's assume that we have x equivalent to 1 here. In this case, your fitted line predicted, your model predicted that when your x is 1, you will have your y to be 3. So this is your y predicted to be 3, right? But if you notice, if you increase your x by one more unit, by 1 unit, so your x from 1 becoming 2, your predicted value of y will be 3.5. So in this case, there is, let's call these predictions of y1, prediction of y2. There's a difference of 0.5, and then that difference, what we call as beta, estimated beta, is just to represent if you increase your x by 1 unit, how much your y will increase. All right, so that's about it. That's how beta is. Now you notice that these equations, the whole equations, depends on the line or the positioning of the line. So the next questions, how to derive the intercept. Sorry, it should be hat here and hat here again. How to derive the intercept and how to derive the beta 1 from these equations. So that would be our topic in the next slide. Let's assume that should be hat here. Let's assume that constant hat, intercept hat is just beta naught hat. And recall that our yi is just the beta naught hat plus beta 1 hat times xi plus epsilon I. So which yi, this one, and these ones are all random variables, right? So in this case, if you want to, let's express this equation in terms of the estimated error, which is this one. The next step, we are about to minimize the sum squared error. What do I mean by sum squared error? Let's break it down into the part. Squared error is just your error here. You just need to square it to be like this. Quite simple. Then you notice that there is like a word sum, right? So you just need to put the summations operator here. So this is the functions, this is the equations of sum of squared error. Pretty simple. The next part, we are going to derive beta naught. I will explain to you the equations here. How do I get that? So in this case, we need to know about the concept of minimizations as well as differentiations, like in the basic calculus. So we have what we call as here our SSR. Why do I call it SSR, not SSE? Because R here, I'm assuming it to be abbreviation of residuals. All right. So you need to differentiate your SSR in terms of your beta naught hat. In this case, is here. If you notice that, beta naught hat should be here. Yeah. If you notice that here you have the chunk here, you have it powered to 2, right? So you have to put it here, make it down here 2, and then after that your beta naught hat actually is accompanied sort of by -1 here. So you put it your -1 as well here. So 2 times -1, and then if you notice again, all of this to the power of 2, you need to minus it off by 1. So you only have power of 1 now. So this is where you get this part. You just rewrite everything here, but it's just to the power of 1 only. Alright? So that's about it for this part. And then because you want to minimize it, you just make it equivalent to 0 in this case. Right? So you have -2, and then if you notice that I actually substitute the not the sigma, sorry, the summations operator inside, you can actually do that. Equivalent with 0, and then here I move it here, become 0 divided by -2 is just 0. And then after that, look at here, this part, yeah? So this part is just the summations of yi. Yi in this case, remember, this is a random variables, right? But in this case, this is constant. This is not a random variable. So the summation of a constant can just express in terms of the number of how many times that constant will appear. So in this case, that corresponds with our sample size. So you just can say that summation of beta naught is just the sample size and times the beta naught hat itself. So minus, in this case, you can put it your beta hat 1 outside of the summations operators, and then in this part is just the summations of xi, which is your random variables again. So let's get a bit more creative in this part. I would like to divide this 0 with n, the sample size, and then of course consequently you need to divide this part by n as well, which is just all expressed here. So this part becomes 0, and then this part becomes the summations of yi divided by n, and then this part becomes this part, and then another part, which is this part, becomes this part. Alright, so that's about it for this step. Next interesting part is that recall that we are working with our samples, right? So it's just the summations of your sample y, right, divided by your sample size. Then it's just your y bar, sample average of y. In this case, the n is offset to each other, so it becomes just minus beta 0. So, and then in this case as well, it's the similar case with this one. It's just the x bar equivalent to 0. And then if I move it here, then if I move my beta naught to this side, I have this part perfectly expressing what is actually beta naught hat. So in this case, we get it here. We get it already. Beta naught hat is actually counted by y bar minus beta 1 hat times the x bar. Now the problem is that we know the value of y bar. You can calculate it in your samples. We know the value of x bar, but we don't know the value of beta 1 hat. So in the next video, I would actually discuss or tell you on how to get the how to calculate, how to count beta 1 hat in terms mathematically, in terms of mathematical expressions. And I think that's about it for this video. Hope it's useful for you. Don't forget to like, share, subscribe, and comment. Give me suggestions, what to improve, where, and then I'm open for opinions. Thank you so much for watching.